All right, welcome to 4.2, concavity and inflection points. Recall we talked about the fact that we can use the second derivative to find concavity, and we talked about the fact that where concavity changes on a graph, it's called an inflection point. So we did that previously, but we looked at the graph. For example, in this first one, I know here that I can tell, let's look at it this way. I can tell that my graph is concave up, and somewhere in here it changes to be concave down. All right, so we call that point an inflection point. Okay, so what we want to do is we can spot it, eyeball it on the graph, but we want to actually find the x coordinate of that point. Okay, the location. So look where that occurs. It occurs here. I have a local min, and here I have a local max. So you will always have an inflection point between a local max and a local min. Okay, always. So you can keep that in mind. Here in the second example, I can see my graph is changing. Here it's concave down, and here it is concave up. So we have this inflection point here, which we're interested in finding. All right, but I don't have any max or min. Okay, so this is an inflection point. So this place on the graph, basically, isn't this a place on the graph where the first derivative is 0, but so we do have a critical point there, but we do not have a local max or min. Okay, so how do we go about finding those inflection points? All right, so what do? Similar process to finding local max and min, except for inflection points, we use the second derivative. Okay, it's not called the second derivative test. That is for local max and mins. Okay, but we find the values where the second derivative is 0. So in order to have an inflection point, they have to be values of x that when you put them into the second derivative, it makes it evaluate out to be 0. Or undefined, which is we talked about, but we will not see that and talk about that in this course. Okay, and the second derivative must change signs at each of these x values. So these x values we call potential inflection points. So this will give us potential inflection points, and then to determine if they are inflection points, we check the second derivative on each side, make sure it changes signs, positive to negative, negative to positive. Kind of like we did with the first derivative test, but we are using the second derivative test. Okay, so let's do an example. All right, here's a function. Let's talk about the domain, which, let me write it down here. X to the 5th minus 5x to the 4th plus 35. So I know the domain, it's polynomial, so the domain is all real numbers, so no concerns there. All right, so we need the second derivative. All right, so the first derivative is 5x to the 4th minus 20x cubed. The second derivative then is 20x to the 4th minus 60x squared. Okay, this is what we're going to use to determine inflection points, the second derivative. All right, and we want to find potential inflection points. those x values, we want to know what makes that equal to 0. So potential inflection points are where the second derivative equals 0. All right, so here we go. 20x to the 4th minus 60x squared equals 0. Another polynomial equation. Solve by factoring. Don't forget to look for greatest common factor first, which is 20x squared. Factor that out. I'm left with x squared minus 3. Whoops, I just saw something. Let me back up the truck. I'm too lazy to go back and edit the video, sorry. You know how I am. This should be 20x cubed. All right, here we go. 20x cubed minus 60x squared equals 0. So if you were shouting at me out loud, you messed up, I appreciate it. Okay, greatest common factor, 20x squared. All right, there we go. So we end up with x minus 3 equals 0. All right, set each factor equal to 0. I know that x is going to be 0 or x is going to be 3. These are what we call PIPs, potential inflection points. I don't know if it's a point on the graph where the concavity changes. All right, so I do a similar test to the first derivative test, but we're now, but it's not called anything special. It's a check for concavity, I would say. So we'll do our number line, and we've got 0, we've got 3. We're checking into the second derivative because we're looking for concavity and inflection points. So you could set up a similar chart, but now we're looking for the sign of the second derivative. So choose a test value in each interval, -5, 1, 10, whatever you want, you can choose. And we're going to test those. So I'm testing -5, 1, and 10. All right, so this is going to be positive, always positive because of the squared. This is negative, so the second derivative is negative on that interval, which means the function is, second derivative is negative, it is concave down. All right. So when I test 1, this one's going to be positive, this one's going to be negative, it's going to be negative on this interval as well, which means it's concave down. All right, and the last interval, 10, I've got positive, positive, positive. So that means on this last interval, the graph is concave up. All right, so if we did a graph or used it to graph, which we don't fully do the graphs from this information like we do in the other calculus class, that would help us. But what we want to know is, are these potential inflection points, are these x values, do we have an inflection point where it changes concavity? Well, I can see it goes from concave down to concave down. So 0 is not an inflection point because it does not change concavity. Okay, it's concave down to concave down. But look what happens over here at 3. We go from concave down to concave up. So this is an inflection point at x equals 3. Okay, so once again, if we wanted to find the actual ordered pair, we would plug that back into the original. So here's my fancy Desmos graph, which you should be using also, or some graphing utility. It's pretty sweet to verify your results. So we can see what happens here at 0. Oh, the y-coordinate would be 35. I already found it. So I can see that at this value 0, we actually have a local max. And here is my inflection point. This is the point where it changes concavity. So it's changing from concave down to concave up. So, pretty cool. And just remember, this is good old Desmos online graphing calculator, desmos.com. Just Google it, right? We can Google everything. All right. Here's some situations that we will come upon talking about critical points and inflection points. All right? Vertical asymptotes. Okay? We can have a graph change from increasing to decreasing or decreasing to increasing at a vertical asymptote. So rational functions, 1 over x squared. We know x can't be 0 because we can't divide by 0. So whatever makes the denominator 0 that does not make the numerator 0 results in a vertical asymptote. Okay, remember it's not a point on the graph. It's a line that the graph never crosses or touches. So if I look to the left of 0, I can see that the graph is concave up, and to the right of that vertical asymptote, oh, it's not. It is also sorry. Duh. Whoopsie. I was supposed to be doing increasing and decreasing. Hello. Rewind. Here we go. To the left, the function is increasing. To the right, the function is decreasing. So if I did my first derivative test, I could see it would change from increasing to decreasing. But the big deal here is that x equals 0 is not a critical point because what? 0 is not in the domain. Okay? In both of these cases, 1 over x, 0 is not in the domain. The domain of both of these functions is negative infinity to 0 or 0 to infinity. Okay? We have a vertical asymptote at 0 on both of them. Okay? So here, it changes concavity, but I don't have an inflection point. To the left, it is concave down. To the right, it is concave up, but we know that x equals 0 is not an inflection point because there is no point on the graph at x equals 0. Okay? So sometimes functions don't have any critical points, or they don't have any inflection points, or they may have one or the other but not both. Okay? $1 million if you can guess. Oh, never mind. I was going to make you guess the function, but I gave it to you. Okay? Remember our exponential function? The domain is all real numbers. Never hurts to review that. And remember the range is only positive real numbers. So anything I put in for x, I get a positive y value. So this graph actually has a horizontal asymptote out to the left. Okay? But we can see that it is only increasing over its domain. Okay? So it has no max or min, which means it has no, I should say no local max or min, has no critical points. Okay? Here's natural log of x. Remember the domain is only positive real numbers, but here the range, the y values are all real numbers. Once again, it's only increasing. Okay? So there is no max or min. And this one, I should say, this one is always concave up over its domain. This one is always concave down over its domain. So it's not changing concavity, has no critical points, no inflection points. But we have a good old parabola. X squared quadratic function will always have one critical point, and which means it will have one local max or min, okay, which occurs at the vertex. We've seen that a lot, okay? So it does have a critical point, which happens to be a local max, okay? But it is only concave down, so no inflection points, all right? So it doesn't always have to have both. All right, or we've seen this several times, a point can be both a critical point and an inflection point. So right here, I know that it is a critical point because the slope of the tangent line is 0. All right, so it's a critical point since the slope is 0. And it is an inflection point because it is concave down to the left and concave up to the right. So it's an inflection point since the concavity changes.